Welcome to another episode of The Outsender, and this time we are indoors and I'm talking in English, and the reason why I am talking in English is because I got a comment in English on a video that was in English called "Antenna Flat on the Ground, Does It Work?" and the comment was regarding the radiation pattern of this antenna that I used in this video. And in this video I took an 45-meter antenna wire that was end-fed using a 91 transformer and a bit of coax, and the whole setup was laying flat on the ground. And I tried the 160-meter band to communicate to a receiving station that was 60 kilometers away. So this receiving station was a Kiwi SDR station, and the distance was 60 kilometers. So what I had the possibility to do was to monitor what happened with the signal that I transmitted by looking at the Kiwi SDR station on the internet, which is really nice with these Kiwi SDR stations that you can do this, and there are so many of them now around the world that you can experiment with stuff like this, which is really nice and which you could not really do in the past then. So on the 160-meter band I got I don't really remember what the signal strength was, but it was fully usable on CW anyway, on 20 watts. And I also tried the same thing and elevated it to an inverted V, where the apex was basically 5 to 7 meters above ground, thereabout anyway. And the result I got on the 160-meter band was the same on the inverted V configuration as it was on the flat on the ground configuration. So that was very interesting. So why would you possibly want to have an antenna flat on the ground? Well, obviously it's super convenient. It's super convenient to end-fed an antenna wire, and it's even more convenient to just run out with the antenna wire on the ground, because when you're done, you just you pull back the antenna and then you just head out. You're done, instead of having to run to a tree and secure it, and the other tree, and elevate the antenna, and you don't have to use poles or anything. So it's very convenient. Why would you possibly want to do that? And this channel is trying to cover radio communication from the perspective that Sweden nowadays is trying to reinstitute or re-establish something which is called the total defense. So the total defense was something that we had during the Cold War, and it basically consisted of two parts: the civil defense, which was supposed to cover all civilian matters, whatever healthcare that you would have, emergency stockpiles and whatever. And then you also had the military defense that would obviously defend the country through force. So basically, like the word suggests, total defense. The entire population was supposed to be part of the defense effort during the Cold War. But then when the Cold War ended, we basically dropped all of this. We downsized the military to a very small part compared to how large it was back in the day. But we also basically totally removed the civil defense, so that was even worse. And now we are trying to reinstitute the total defense, and I believe that the civil side is lacking a lot of experience that we in the military side has. And by we, I mean that I am an army radio operator, so I have the military perspective of radio communication, obviously. And then when I look at the civilian side, from a crisis and emergency disaster communication perspective, I see a lot of radio communication equipment and systems that are super vulnerable to jamming and geolocation, direction finding, or geolocating actually. So a lot of these civilian systems are not really designed to use in emergencies, even if they are considered that. So that's a little bit about what this channel is about, and it specifically focuses on HF. and then what I'm usually calling signature adapted HF, where it becomes even more difficult to direction find. HF is super difficult to direction find or geolocate as is, or skywave communication is super difficult to geolocate. But if you use the concept that I call the Zenith concept, then it becomes even worse for an opponent to try to geolocate you. And that could be very important from a total defense perspective. That's what I'm thinking. And I'm also thinking that like in the past, the military defense and the civil defense will have to cooperate in its effort to defend the country, basically. So that's something that is always in the background on this channel, and it would apply to any country in Europe and in any country in the world, actually. So that's but we in the West, most Western countries, high-tech Western countries, we have not a very good understanding of HF from a contested environment perspective, a hostile environment perspective. There are a lot of amateur radio operators that are very skilled and everything, but I'm trying to not take the military, the radio operator, army radio operator kind of stance that, oh, it's amateur radio, that's, doesn't apply here. And it's basically downsizing the importance of amateur radio, I think, in crisis communication, where you usually have a different mindset and different thinking when you're talking as a signaler or a radio operator, because basically it's a professional job being a radio operator, while amateur radio is a hobby. But since I'm obviously an amateur radio operator with the call sign Sierra Alpha 6 Mike Whiskey Alpha, this is a huge interest for me. And since we have this total defense effort, I want to, just share my perspective on things and, try to contribute something to the emergency communication field, basically here. I'm trying to, get the focus on radio communication back, not this vulnerable civilian type of radio communication, but more robust communication, and HF is part of that concept. So back into this then. So the comment I got on this video was regarding the radiation pattern on this antenna of the end-fed 45 meter antenna with a 91 transformer, and the comment, we can scroll down to this comment then. It was from Cross Country Wireless, G4HYG, Chris, and he makes a really good point here, and that's why I want to do this video then. So he says that laying the antenna on the ground makes it work like a beverage antenna, where the horizontally polarized wave is cancelled out and the antenna only gets directional vertically polarized wave. I did a demonstration. Then he has a page here with this experiment explained. So here we have a radiation pattern on this model, and he used a 40 meter antenna wire. I used a 45 meter antenna wire, so it's basically the same. It's not a huge difference. So and this one was also laying flat on the ground, and it was obviously end-fed since it's a beverage antenna. So what is a beverage antenna? Well, a beverage antenna was invented by Harold Beverage. I may be wrong there, but I think his name was Harold Beverage. And anyway, what it is, it's what we usually call a traveling wave antenna. So basically you have the antenna wire, and the wave, it travels along the antenna wire, but when it reaches the end of it, it doesn't bounce back, it doesn't reflect back, it doesn't become a standing wave like it does in most other type of antennas, because usually at the end of the antenna you have a terminating resistor that is grounded, or the antenna wire is so long that it basically never reaches the end. That's it's an infinite long antenna, basically. That's the theory anyway. And if you have a very super long antenna that is maybe 1 kilometer or something, and you're using like the 80-meter band, then the signal strength would more and more dissipate into the ground and into the atmosphere instead of reaching the end in any significant strength. So it would never bounce back and cross this standing wave in the antenna. So it only travels in one direction basically. And then you have a lobe that travels along this wave, I don't have anything good right now to demonstrate this with, but we are going to look at the radiation patterns shortly here then. So I agree with everything he says, but what he says is, well, that's my comment. Basically what he says is that it's all true, but it depends on basically 3 factors. And it depends on the length of the antenna wire, it depends on the frequency used to transmit or receive, and it depends on the height above ground. In this case, the height above ground is obviously, it's laying flat on the ground. That's what we are going to discuss then. But we're talking about the frequency and the length of the antenna. And obviously here I think it says 3.6 megahertz here, and it obviously runs along the x-axis here and gets this radiation pattern. And then you can see that this near vertical incidence skywave type of communication that we want to have, which is basically straight up into the sky, it doesn't seem to be that much energy there in this radiation pattern. You get a little bit fooled by these models unless you look at the actual numbers. So it's not that directional anyway, but let's look at this then. This software is called it's XNEC2C, and it's NEC2C. It's NEC2 implemented in C programming language. And this is this is an open source software. It's not super good in any way. You basically fill in these NEC cards, if you're familiar with this, with the wire segments and everything. So this is not a NEC how-to video, but you can see a radiation pattern here, and the frequency is 1.8 megahertz. I believe it starts on that. And we have one wire in this case, and the problem with NEC2 is that you cannot have an antenna on or in the ground in NEC2. It doesn't support that. Actually, the model is not supposed to be super correct when you have it very close to the ground either. So I actually got it down to 4 millimeters in this case. So that's the lowest I could get it without the NEC complaining that it was too close to the ground. So that's pretty impressive. I'm not so sure that I've got that low before actually, so that's pretty good. But anyway, this antenna wire is 44.5 meters, and it has the conductivity of steel, or stainless steel in this case. And the wire diameter is 2 millimeters. And the reason why I have this 44.5 is that actually I have a stainless steel antenna like this that is 44.5 millimeters. 44.5 meters long, and I just wanted to demonstrate that it's not that big of a difference with a stainless steel or steel antenna compared to a copper antenna if you have the diameter, the appropriate diameter on the steel wire. If you have a very thin steel wire, the resistance is a lot larger or higher than it is if you increase the surface area. If you increase the surface area of a steel wire or any wire material, then the resistance drops. And that's why this 2 millimeter antenna wire is only half a dB. It's like, I think it's even less than 0.5 dB difference compared to a copper wire of the same diameter. That's about it. And this one is 4 millimeters above ground, and it's 44.5 meters long. And then we have this radiation pattern, and I also have, this is an excitation card, and in this case it's excited at the first segment which means that it's end fed, you know, here. And you could also feed it in the middle. There are 15 segments here, so if you have the eighth segment, save it, then you have a dipole basically, or a non-resonant dipole actually. So in this case you have a nice round bubble, but if you end feed this length of wire on this frequency, you can see that the whole bubble, it basically shifts a little bit. It becomes a little bit directional. And that's an issue when you want to do near vertical incidence skywave, and you basically want to send as much energy as possible straight up into the sky. So that's a caveat that you have to think about when you end fed an antenna and you want to use it for NVIS. That's a very important perspective then. So in this case, we are talking about the 160 meter band, and we can actually just play this. And you can see that when the frequency increases here, the radiation pattern also increases, and it becomes more and more directive. Let's do this again then. So at here, basically, well, we can go up to the 80 meter band directly. And now it starts to look exactly like this. Not really exactly, but you know, it reminds you about this. So it has a huge lobe here in front, and it doesn't have that in the other direction, and it's going to be like that. Let's see if I get this straight. So the antenna wire runs in this along the y-axis here, and now we're looking 90 degrees, you know, just straight down into the antenna. And we can see that we have a gain or a loss of minus 24.75 dB straight up into the sky. So that's not very good. Then if we rotate this one, well, you can see that, you know, even here, even in the end here, now it's 26 dB. So it's not, you know, it's not huge difference, but obviously if we have like the 80 degrees here that we were interested in, then that becomes an issue, obviously. So let's just go around, and if we have 80 degrees here, we have like minus 21 here. So we have more gain in the direction the antenna wire is going compared to here then. Well, now we're going to have 80 here. Well, it's this software is a bit tricky, so what am I doing? Minus 90 maybe. Yeah, like that. So minus 31 compared to, so there's a 10 dB difference. That's not very good. So for near vertical incidence skywave and this frequency, when the antenna is laying flat on the ground, that's not optimal, definitely not. But on the 160 meter band, we don't have that issue at all. We basically, when we have some directivity in it, but if we look here, minus 18.91, and you know, looking straight in at minus 18.60, so that's not a half a dB difference even. That won't make any difference to this antenna, to the radiation pattern, or the whatever. Even if you have like 80 degrees up here, you have 80 degrees here or something, then you have minus 19. And if you do it like that, you have like minus 8, not even, you know, it doesn't really make any difference in this frequency. But if you use the 80 meter band, you obviously have something completely different if someone wants to. So you can see that, yeah, we basically have a directional antenna. But if we look into the lobe here, it says minus 16 compared to 90 degrees. Minus 16 compared to minus 24. So, well, it's like almost 10 dB difference. So it's slightly more than an S unit difference from the lobe then. but still 24, minus 24 here compared to the 80 meter band where they're minus 18. It's not a huge difference. But then we're going to switch to another antenna here, and this is the same antenna. The only difference here is that this one is 2 meters above ground. So it's the same antenna, same connectivity and everything, but it's 2 meters above ground. Now it starts to look, it looks exactly like a dipole basically. It has all of the energy goes straight up into the sky. And here you have a better gain also. You have like a 10 dB difference. So elevating the antenna always makes a difference. And you should, if you can, you should always elevate the antenna, obviously. So minus 8.49 dB. And then we can take the 80 meter band again. And now we see this. Now it's a nice bubble again. It has some directivity, but it's you know, the directivity is less than half a degree here. So yeah, and the gain is like minus 3. So now we are starting to see some improvements here. But if we take this even further, we go up in frequency here. Then we're starting to see more and more directivity. We could ramp this up further. And eventually you reach a pretty sharp cutoff somewhere around here, 4.5 megahertz. But the gain is still, you know, still more than it was on the 160 meter band, so it's still, you know, completely usable as an NVIS antenna, even if the gain is not, you know, not minus 4 point whatever. It's minus 6 or minus 7, but you can ramp up this further, and eventually it will drop very sharply, and then you would have, you know, on the 60 meter band, you have a pretty, well, it's still usable for NVIS. It's not that bad actually, but we should have this like 90 degrees again. Let's see if we can do that. You know, it's not that bad. It's just a 1 dB difference compared to the 160 meter band. So, you know, not just because it has this radiation pattern doesn't mean that it has a sharp null in the middle. It's not a vertically polarized antenna. It's still a horizontally polarized antenna, but it has a radiation pattern that looks like a beverage or a traveling wave antenna. That's basically it. So if you ramp up this further to the 40 meter band, here we're starting to see some serious drop in the null. And now you can actually argue that, well, it's almost like a vertically polarized antenna in this case. And yeah, it is, even if it doesn't have this donut shape that you know, a vertically polarized antenna has. But it definitely has a pretty sharp drop in the middle here. So that's not what we want for near vertical incidence skywave. However, Sweden is pretty far north, and I don't think there has ever been a case here where you actually could use the 40 meter band or 7 megahertz for near vertical incidence skywave communication, at least not without a skip zone. So if you would have like a 60 degree link to whatever, Stockholm or something, from the west coast to Stockholm, cross country, or from the north of Sweden to the south of Sweden, then you would definitely, well, I probably think that you would probably have a skip zone in between there somewhere, and then it's not near vertical incidence skywave anymore. So we're talking about communication up to from 0 to 200 kilometers. That's basically what this concept is all about then. That's the area that we want to cover in both in a crisis situation for emergency communication in the area and throughout, you know, from a military operational perspective. The distances are not that long in military operations. Depends on which level you're on, obviously, but on the operational technical level where the conflict is, 200 kilometers is a very long distance, and then you're outside of the conflict area basically then. So yeah, so 7 megahertz would not be possible to use NVIS. So then basically you could end up with having a critical frequency an FOF2 frequency of 5 megahertz here in the summer, in the middle of the day, or like a couple of hours after 12 o'clock noon, then you could maybe have 5 megahertz as a critical frequency and actually use it for near vertical incidence skywave. But that doesn't happen very often. Usually it's below this, and usually you have like you have an FOF2 of 4.5 or something like that. That means that you would have to use the 4 megahertz frequencies thereabout, and that would work for near vertical incidence skywave then. So this antenna, the 45 meter antenna, it's basically designed for northern hemisphere, northern countries where we don't have that much sun, and the critical frequency, the FOF2, is pretty low. So it's not designed for near vertical incidence skywave in the equator, for example, where you can have an FOF2 of like 10 megahertz or 12 megahertz even, or maybe even higher solar maximum. So then you would have the F2 layer would be seriously ionized, and in that setting, the D layer, which dampens the low frequencies, it would cancel the 160 meter band, the 80 meter band, and maybe even the 40 meter band. There could be a scenario in mid-Europe or southern Europe, or in the equator, also around the equator, where when the D layer disappears at night, it opens up for the 160 meter band, the 80 meter band, and everything. And then you maybe want to use those bands during the night, because they probably work very well when the D layer disappears, and you still have the F2 layer that is highly ionized, so you can have extremely high signal strength on the 80 meter band perhaps. And then maybe if you want to use the same antenna for day and night frequencies that are so far dispersed, and we cannot do this here in Sweden because we don't have an FOF2 ever that high, and we usually can, well, maybe you actually can have an FOF2 that is even lower than the 160 meter band. Far up north during winter, when there is not very much sun, the FOF2 middle of the night at 2 a.m. or something, the FOF2 can actually be like 1.6 or something, and then you cannot even use that. So in that setting, if you want to have a very long antenna or very short antenna, whatever, and use a large span of frequencies, then you would have to use either 2 antennas, or you can have this antenna wire that we have here, the full length, and you can make links in it. So for instance, if let's take this one. This is antenna on the ground, of 4 millimeters on the ground. So we go back to 80 meter band again. Let's say that we want to use this antenna, or the same type of antenna anyway, the same antenna wire. We just want to cut it somewhere. So we shorten the antenna so it's more appropriate for near vertical incidence skywave. Then we can just introduce a link in it. So we are going to, what could we have? 21 meters is a pretty standard length of random wire, I think. You get a pretty solid, pretty good standing wave ratio in a coax with a 9:1 transformer with a 21 meter long antenna, I believe, on the amateur radio bands. So in this case, here we have the 80 meter band, we have the 21 meter antenna. So in this case, it would basically simulate having a link in the antenna that you disconnect if you want to use the high frequencies. And here you can see that you have a nice bubble on the 80 meter band with the antenna that lays flat on the ground. So here I have modified one of the 3 variables that would affect the radiation pattern. I have modified the length of the antenna to accommodate the frequency that I want to use. So now this scenario is different. I can probably continue using this up until maybe like 7 megahertz here. And if I want to be able to use the 30-meter band for near vertical incidence skywave around the equator in the middle of the summer, basically, then I would have to have an even shorter antenna. So maybe you need like you could use 2 links in this antenna or something. 10 megahertz. And then you see that on 10 megahertz here you have this nice bubble, and you have like minus 10 dB. Well, with a 9-meter antenna wire flat on the ground. So you could obviously use this one on 7 megahertz also, but it could be minus 18. Okay, maybe not that bad then. The problem is that maybe your antenna tuning unit won't really like this short antenna. You could end up needing a lot of inductance. So the inductance coil in the antenna coupler in the transceiver, or the external antenna tuning unit even, you could have a hard time matching short antenna wires. So that's why you basically need to change the length of it. You could obviously, wind up the antenna. If you roll it up tight on a wind or something, you can have the same, basically the same result as this, if you don't want to use links in it. But well, we're going to go back to the scenario where I am at, which is that we don't have that many frequencies to play around with. And in this case, I could still use like up to 3 megahertz without a problem, even if it doesn't look very good, especially not on the back then. What could we change more? We could obviously elevate it even more, and then we only, get a better radiation pattern. So we have much better gain here if it's 7 meters above ground, and we still have the same. It's the same antenna, 44.5 meters. It's 7 meters above ground, and now we can have the 80-meter band. We see that now it's a very nice bubble here compared to this one, so now I have modified the height above ground. So then we can even go further, and it's usable up to, maybe 4.8. Well, actually, it would be usable even further. Well, it would be usable on the 60-meter band, or maybe not really, depends. Well, almost 5 megahertz anyway. Maybe not the 60-meter band, that it drops off even more there. But then it's elevated 7 meters, and you probably don't do that. 2 meters is a very good height. It's something that you can elevate it without needing to throw a bag up into a tree or something. Well, that's something to consider when using end-fed antennas. It's a compromise, but the radiation pattern depends on the length of the antenna, and the frequency that you use for the antenna, and height above ground. And you should always elevate it if you can. And it's worth considering then that if your antenna is nearing half a wavelength, then it will have it will be very directional, or pretty directional, if it's very low towards ground. And if it's above half a wavelength, the antenna wire, and it's more than 2 meters above ground, then it will start to you will start to experience some directivity there. So you cannot really use one antenna wire for all scenarios. However, you could use a dipole. Why not use a duplet, non-resonant dipole antenna instead? Well, obviously because it's not as convenient as an end-fed antenna. So let's do that instead. We have this excitation card here, and feed it in the middle again. And now obviously we have this bub. Oh, sorry. Let's go up to 8-meter band. Now we have this nice bubble here, and we have better gain also. I believe, yeah, probably. There's a lot better gain here. So that's one way you could do it. And if you have an antenna tuning unit for this, you could obviously, you know, just lay a dipole on the ground. And it's also a duplet fed with a ladder line. It's very simple to you know, run out with and pull back in also. So it's really not that big of a hassle. But an end-fed antenna is obviously much simpler if you want to elevate it. You just you can do near vertical incidence skywave with a sloping antenna, so you just need to elevate one leg of it, basically, anyway. So yeah, this is possible, but you cannot feed it with coax in this case because of very ridiculously high standing wave ratios. So you have to use ladder line to do it, and then you need to have a transformer or something that could actually work with this. In the antenna tuning unit that you have to use, an antenna coupler that you use with a ladder line non-resonant duplet to be able to use the whole frequency span, we have to have a huge matching ratio also. So there's a lot of problem there that you may not be able to match everything with a duplet. So that's a consideration also then. So why not use resonant antennas for this reason, or use an antenna that is resonant on each harmonic? Well, the main reason is that in the crisis situation, if you as an amateur radio operator will sit as a professional radio operator in some way or form in the total defense effort, basically, then you would probably be assigned by the broadcasting agency frequencies that are basically all over the place. It's not like the amateur radio band. It's not designed in any way or form to be multiples of harmonics. It's you get assigned channels, and the number of channels or frequencies that you would get assigned could be like 50 or 200, and then you cannot use a resonant antenna for that. It would be totally impossible. You would have multiple of resonant antennas. So either you have to use a very wide band antenna that you use for this scenario, and it's basically like what's it called? It's a carpet antenna. I forgot what it's called in English. So well, it's basically like a mesh of antenna wires of different length. So whatever you feed into this antenna, it basically presents itself as 50 ohms, regardless of frequency in the HF spectrum, from 1.6 megahertz up to maybe 30 megahertz. The radiation pattern differs obviously in this antenna, but it's very convenient. However, it's, it may weigh like 50 kilos, the antenna. That's an issue then. So if you need to deploy an antenna fast and you want to be portable, it has to be usable. And that's one of the reasons that all green military radio transceivers have an internal antenna coupler inside it, an antenna tuning unit inside of them that is used to be able to match basically an antenna. It's pretty wide, usually. Most of them are pretty wide. And if it doesn't have an internal antenna coupler, you usually have boxes, external antenna couplers that are automatic when you connect the manpack radio to an amplifier. So so that's an issue then. And you would also have day-night frequencies, and you would have a set of frequencies that you would hop around on, basically depending on QRM, if you have some interference, or if you need to follow along with the conditions, throughout the day, and you need to maintain a link to a certain distance throughout 24 hours, then you have to have day and night frequencies, and they will not fit into a harmonic perspective in that way. So resonant antennas will be super difficult. You could obviously use tilted terminated folding dipole, or terminated folded dipole, but it's not resonant either. It just looks like it's 50 ohm or pretty close to 50 ohm, and then there's a terminating resistor in it that dissipates some of the energy. So that's one way to do it, but it's obviously not resonant then. But it's pretty simple because you can use it without a tuning unit and hop around on frequencies pretty rapidly, which you would probably be assigned an ALE, automatic link establishment radio, for this purpose also, that would automatically find the best channel, the best frequency to use according to link quality. Then you just call up a station and you just lift the headphone and start talking, basically. That's it for this episode of the Outsender, and if you enjoy this episode, please give it a thumbs up and consider subscribing. I really appreciate that. And you can hit the bell down there to get notifications when the next episode is public on YouTube. And if you want to see some of the episodes before I publish them and some other material, and you also want to join the Discord community, then please consider becoming a Patreon on www.patreon.com/outsender. And it doesn't matter which tier you're in as a Patreon member, you get access to the Discord community regardless of which tier you're in. So, if you want to be part of this Discord community, then please consider becoming a Patreon. That's it for this episode, and as usual, I say 73, end of message, out.